Hello Pre-Calc BC. These are our Day 10 notes. We're going to be talking about some more mathematical induction. And these problems are going to be a little different than the ones we did yesterday, but we can still use mathematical induction to prove these. So our first question says, using mathematical induction, show that 3 to the n minus 1 is divisible by 2 for all natural numbers. So we are going to start again with condition 1. We're going to let n equal 1. So I'll just plug the 1 in. And this will give us 2. And we do know that 2 is divisible by 2. So I'm just going to write that note. This is definitely divisible by 2. All right, let's try that again. This is definitely divisible by 2. Okay, so statement 1 is confirmed. So now condition 2, or statement 2, we are going to assume that n is some value k. And to do that, we're going to do just as we did in the past. We're going to plug a k in to this statement here. Okay, and again, we are going to assume that this is also divisible by 2. Okay, so at this point, this is an assumption. But again, if we can prove that the k plus 1 value is divisible by 2, then we can say that all of these are divisible by 2. So now we're going to prove true for k plus 1. All right, so how do we do that? Essentially, we are going to start the same way we have in the past. We're going to plug a k plus 1 in for k, or in for n, if you want to look at it that way. This is, again, just the next term after the kth term. What's weird about this, though, is that there isn't, like, it's not equal to anything. And we can't prove that two things are equal to each other like we did in our problems on day 9. So we need to somehow prove that this is divisible by 2. So the main way we're going to do that is we are assuming at this point in time that this guy right here is divisible by 2. So we want to somehow get back to this, somehow get a 3k minus 1. And the way we can do that, and at first this is not going to seem super obvious, but the way we can do that is breaking this apart. So what you should know is that you can make this into 3 to the k times 3 to the first. Because if you have the same base, you can add those exponents and you'd get that k plus 1. And then I'm just going to bring down this minus. All right, so I want you to be careful though, because we can now see we have a 3 to the k minus 1. But remember, right now this is a package deal, okay? This is one thing. So you can't just say, oh, we're done, we got a 3 to the k minus 1. We are not done, okay? This 3 to the k minus 1 is just, there's just a 1 in front of here, all right? 1 times 3 to the k minus 1. This is a 3 times a 3 to the k minus 1. So that is an issue. Remember, this 3 is not multiplying to everything, okay? This is not like distributive property. It's just multiplying to the 3 to the k. So now, here's what we're going to do. We are actually going to break 3 to the 3k up into 2 pieces. Okay? Going back to a problem we had on day 9, we kind of did combining like terms with these exponentials. In fact, I'll go find it right now. Oh, nope, I don't have it anymore. But basically we had said, hey, pretend this 3 to the k was an x value, and then we added two things together just like we would like terms. So what we're going to do instead is we're going to break this apart. 3 times 3 to the k, and you can pretend this is an x. This would be the same as a 2x plus a 1x. Yes? 3x would be the same as 2x plus 1x, which means this is a 2 times 3 to the k plus 1 times 3 to the k. And again, you can see if you combine like terms here, 2 3 to the k plus 1 3 to the k would give you 3 3 to the k. Now, why does that matter? Because now I can show that I have this right up here. Okay, so let's go back now. I am taking this guy right here, oops, excuse me, this whole thing right here, and I am rewriting it as 2 3 to the k plus 1 3 to the k. All right, again, you could combine like terms to get that 3 3 to the k. And then I'm just going to bring down that minus 1. And now I want you to look at what you have. You have this, and you have this. And this right here, well, this is for sure divisible by 2 because it's a multiple of 2. And this we also have assumed is divisible by 2. All right, so again, this is what this is saying. All right, we have shown that if k at the k term is divisible by 2, then the next term for sure is also divisible by 2. Okay, so if this guy is divisible by 2, then the k plus first term also is divisible by 2. And since we showed the first term is divisible by 2, that will follow that all terms afterwards will be as well. You do need to show me that these are both divisible by 2. You need to make that comment so I understand why we're done. And then we'll just go ahead and we'll use our statement like we normally do. Conditions 1 and 2 are met. So the statement is true for all natural numbers. All right. So again, it is a little different. It involves some special thinking here. Okay, so now let's try number 2. Using mathematical induction, show that n squared minus n plus 2 is divisible by 2 for all natural numbers. Okay, so again, we have a divisible by 2. Let's start with condition 1. We're going to go ahead. We're going to let n equal 1. And we're going to plug this in. And that gives me a 2, which is divisible by 2. All right, so now I am going to assume I'm going to let n equal k. And again, I'm just going to plug this in. And I am assuming this is divisible by 2. All right, right now it's an assumption. But once I can prove true, for k plus 1, then I know that it's going to be true for all of these. All right, so in order to do this, I'm going to take k plus 1, and it's going in place of n, or in for k, however you want to look at it. And then what I'm just going to do is go ahead and FOIL this out and distribute. Watch your signs, please. And then I know that it is tempting to go ahead and just combine all your like terms. But what we want to do is we want to look for this, because right now we are assuming that this is divisible by 2. And if you look, you do have a k squared minus k plus 2. So I'm just going to group those together because I know that this is divisible by 2. Or at least I'm assuming right now it is. And so now I'm going to put the rest of it together. There was a 2k plus 1 minus 1, which 2k plus 1 minus 1 is just 2k. This I also know is divisible by 2 because it is a multiple of 2. All right, so here's the situation. We have that the first term is divisible by 2. And then we have assumed that term k is also divisible by 2. And if that is true, then we now can see that the term k plus 1 is also divisible by 2. So since we've just shown that if a preceding term is divisible by 2, then the next term is definitely divisible by 2. And we have proved this first one, n equals 1, is divisible by 2. This is now true for all natural numbers. Okay, conditions 1 and 2 are met. So our statement is true for all natural numbers. All right, and we have one more, which is more similar to yesterday's, but it's still going to be a little bit different. Using the principle of mathematical induction to show that the given statement is true for all natural numbers. So what makes this one different is that you can see each of your terms are multiplying instead of adding. All right, but we can still use this. So let's start the way we always do, let n equals 1. So again, you can either just take this, which is 1 minus 1/2, equals plug in a 1 over here, or you can plug in a 1 to this one and plug in a 1 over there. Either way, 1 minus 1/2 is 1/2 equals 1/2, check. This is going to be 1 minus 1/2, which is 1/2 equals 1/2, check. All right, so either way you want to look at it, you're going to go ahead and you're going to get that n equals 1 does work. Okay. All right, so now we're going to let n equal k. And this is kind of annoying to write it all out, but we're going to do it anyways. If you want to just put those, that's fine. And again, we're just plugging in a k for n. Okay, so this is what we're assuming is true. But now we need to prove true for k plus 1. Okay, so the first thing we need to do is we need to get to the k plus 1th term. Remember, this is the kth term right now. So we're going to say 1 minus 1/2, 1 minus 1/3, dot, dot, dot forever, 1 minus 1 over k plus 1. Again, that's the kth term. 1 minus 1 over k plus 1 plus 1 equals, and okay, so this was for the kth term. All right, so now we're doing for the k plus 1th term. So you, again, need to go ahead, change k to a k plus 1. All right, because as you would do this, each number, as you would go to a new term, the n would advance, right? So if you were finding the first term, you would plug in 1. If you were finding the product of the first 2 terms, n would be 2. So that number is getting bigger every time for every term that you do. If you were doing the multiplication up through 3, you would plug in a 3. So since we're now going one more term, we need to have one more bigger number right here. Okay, so now if you recall, we just said that this whole thing is equal to this. So we are going to take this whole thing and replace it, which gives us 1 over k plus 1 times 1 over, and now you can go ahead and combine. This is k, or 1 minus, excuse me, there's a 1 minus there, 1 over k plus 2. And this we're going to leave as is. All right, so there are a couple ways that you can do this. From here, one thing that you can do is go ahead and get a common denominator right here. So that would just be a k plus 2, k plus 2. And that would give us this. And then you would have a k plus 2 minus 1 over k plus 2. All right, that's just getting a common denominator. And again, you want to make sure you're showing all your steps, okay? You can't skip steps. Even if in your mind you're doing more things than one at once, you've got to just slow it down and do each step so that I can grade it. All right, so k plus 2 minus 1 is just k plus 1 over k plus 2. And this one actually is not bad at all. You can now see that your k plus 1s are just going to cancel out, and you're left with a 1 over k plus 2. And finally, after doing these the other day, you should say, oh, well, now I'm just going to expand this k plus 2 and make it k plus 1 plus 1. And there you go. And then just don't forget to write your statement since conditions 1 and 2 are met or are true, so statement is true for all natural numbers. Okay, now before you go, I just wanted to show you one more way to do this. And it might not seem like the best way for this problem, but this is a strategy that you could use for other problems. Since you have this fraction out front here, this is really like you could do distributive property. So 1 over k plus 1 times 1 is just 1 over k plus 1. 1 over k plus 1 times 1 over k plus 2 is 1 over k plus 1 k plus 2. And then what I would do is I'd say, oh, hey, I need to get a common denominator now. So I'm going to multiply this guy times the k plus 2, k plus 2. And again, I'm not saying this is the best method for this problem, but this is a strategy that can work for other problems similar to this. Okay, and then, okay, please, 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 you cannot just cancel these k plus 2's. All right, there is subtraction here. All right, don't even think about canceling those. You're going to need to combine. And I realize, I guess that goes up there. This is k plus 1 over k plus 2, k plus 1. All right, and now you can go ahead and cancel the k plus 1's. And you're left with a 1 over k plus 2, which again, at this point, I'm completely off. But then you could rewrite your k plus 2 as a 1 over k plus 1 plus 1. Okay, so that would be another strategy you could use. All right, I hope this was so thrilling for you, and I hope you have a wonderful day. Bye-bye.